Picture this. The precise millisecond an EV is involved in a high-speed collision. Now, we've all heard about crumple zones and airbags, right? But there is a hidden, invisible war against raw electricity happening in less time than it takes you to blink. Welcome to this explainer. Today, we're tearing down the extreme engineering behind an EV's post-crash high-voltage release. We're going to be talking about microsecond-level battles, catastrophic physical forces, and the frankly ingenious safety nets designed to save lives when absolutely everything goes wrong. Now, everything we're looking at today revolves around a terrifying ticking clock. In the automotive industry, there's an ASIL D safety mandate, which is literally the highest possible risk classification. This mandate dictates that the exact moment a car detects a crash and triggers the airbag, it has exactly 2 seconds to drop the DC-link capacitor's high voltage safely below 60 volts, or down to less than 0.2 joules of residual energy. And if it fails, you're looking at lethal electric shocks for passengers and first responders, massive thermal runaways, and severe fire risks. No pressure, right? Okay, let's dive right into this. We're going to break this down into 5 parts. First, the physical root causes of discharge failure. Then, architecture and redundancy. Third, DFMEA design controls. Fourth, PFMEA process controls. And lastly, DVPNR validation. So, Section 1, root causes of discharge failure. Or to put it simply, the brutal physical reality of a crash. When things go sideways during an extreme crash, the system can actually fail across 4 distinct dimensions. First up, signal path interruption. The physical hardwire between the airbag control unit and the motor controller can literally just snap from a 50G impact, or get blinded by extreme electromagnetic interference. Second is contactor welding. If a short circuit happens right before the crash, high-temperature arcs can actually micro-weld the main relay shut. This means the battery stays connected, creating an infinite power loop that just burns out the discharge circuit. Third, direct physical damage. Circuit boards violently bend, snapping the solder joints on MOSFET switches, or the 12-volt auxiliary power completely drops out. And fourth, actually, this one is absolutely wild. The sheer high-frequency resonance of the crash can shatter the microscopic quartz crystals inside the microcontroller. That locks up the processor's clock and freezes the entire software state machine before it even has a chance to trigger the discharge. Moving right along to Section 2, architecture and software redundancy. This is how we build the failsafes. To survive that kind of chaos, engineers rely on dual-channel redundancy. If a wire snaps, channel 2 is there, relying on high-priority CAN-FD network software messages. But what's really interesting here is channel 1, hardware direct. The crash signal is hardwired straight into the system basis chip, or SBC. Think of this as a rebel hardware bypass. If the main processor is shattered or locked up like we just talked about, the SBC's internal hardware autonomously triggers the discharge in under 100 microseconds, completely bypassing that frozen main computer. But, what if the physical discharge resistors themselves just get completely pulverized in the crash? Well, this is where the engineering gets brilliant. The system detects that the voltage isn't dropping fast enough, so, as a software backup, it executes a hybrid voltage modulation strategy. It shoots massive, symmetrical, direct-axis current straight into the electric motor itself, locking the magnetic field at 0 torque. It literally turns the motor's stator windings into a giant energy-absorbing sponge, using stator copper loss to safely drain the battery's energy in just 1.5 seconds. And here's an absolutely crucial detail. Once the system successfully wrestles that voltage down below 60 volts, using isolated sensor channels to verify it, of course, it does one final, permanent thing. It writes an irreversible DTC P0A0 default code deep into the EEPROM memory. This permanently locks the system out. No one and no glitch can repower those high-voltage lines. And that is an absolute necessity to make sure that first responders can safely cut into the vehicle with the jaws of life without facing a lethal shock. All right, Section 3, Bulletproof Design Controls, or DFMEA measures. You can't just slap these components onto any old circuit board. The macro-level layout is strictly tactical. Step 1, all active discharge switches are placed in what's called the safe core area, which is the exact spot calculated to experience the least physical bending during a crash. Step 2, engineers literally cut stress relief slits right through the PCB around these circuits to isolate them from impact ripples. Step 3, heavy components, like those massive 50-watt aluminum resistors, get rigid reinforcement pillars installed underneath them. This armor plating guarantees the components won't tear themselves off the board during a brutal 50G impact. And it's not just physical trauma, right? It's electrical chaos. The electromagnetic noise of metal crushing and wires shorting is just immense. So engineers mandate isolation chips with a common mode transient immunity, greater than 100 kilovolts per microsecond. Combine that with a negative 5-volt bias to actively anchor the discharge switches closed until the exact right moment, and you prevent the circuit from being accidentally triggered by the high-frequency electrical noise of the crash itself.
Even the tiny stuff is locked down. The bill of materials heavily vets things, forcing the use of Class 1 C0G ceramic capacitors. Why so specific? Well, in a crash, components can heat up rapidly and asymmetrically, but these specific capacitors maintain a plus or minus 0.1% precision and have near zero temperature drift. This guarantees the system doesn't read a false voltage spike due to heat and panic, preventing some really deadly miscalculations.
Next up, Section 4, Flawless Manufacturing Processes, are PFMEA process controls. To make sure the build is actually flawless, 100% of these control boards get hit with a 3D X-ray or acoustic scan on the assembly line. They're inspecting the microscopic solder joints. The standard, maximum allowed voids, which are basically empty air bubbles in the solder, must be less than 5%. Why? Because if a crash hits a solder joint that's mostly hollow, that microcrack instantly grows, severing the connection and completely disabling your safety discharge system. The physical assembly is just as obsessive. High-voltage bus bars use phosphate-coated bolts locked in by servo torque angle machines to guarantee an ultra-low physical resistance of less than 5 microohms, preventing lethal arcing heat. And before any unit leaves the factory, it faces a 100% automated end-of-line test. The system literally injects a simulated crash pulse and maps the exact discharge time. If it doesn't nail that precise 1.2 to 1.5 second curve, the system flags it, locks it, and it never goes into a car, period. Finally, we hit Section 5, Extreme Production Validation, also known as DVPNR. And this brilliantly illustrates the sheer torture these components endure before production. First, rapid temperature swings from -40 to positive 125 degrees Celsius combined with violent 3-axis vibration for 500 hours, with 0 signal drops allowed. Then, the mechanical shock test, a literal 50G impact simulating a horrific crash. Even after all that, the system must still discharge in under 1.5 seconds. And finally, my absolute favorite, the hardware-in-the-loop dyno fault test. They run the motor at a screaming 12,000 RPM, simulate a crash, and deliberately blow up the virtual discharge resistors just to prove that the software backup we talked about earlier can still recognize the failure and safely drain the system in under 2 seconds. So we've tracked this incredible 2-second lifeline all the way from the destructive forces of a crash, through hardware bypasses and motor winding sponges, all the way down to micro-level PCB slits and X-ray scanned solder joints. The level of unseen engineering dedicated purely to those post-crash seconds is just staggering. Which leaves us with a pretty provocative thought. If a system is engineered this aggressively to safely dissipate lethal energy in 1.5 seconds while enduring 50G forces, what other invisible safety nets are hidden inside your EV, just waiting for the exact moment you need them most? Thanks for joining me on this explainer, and keep exploring the incredible engineering all around us.